Welcome students. In the previous two lectures, we have seen a lot of information about terpenoids. Now we are proceeding further for the study of one terpenoid. It is a citral. It is an aldehyde. Its structural name is 3,7-dimethyl 2,6-diene-octanol. It is an optically inactive, acyclic, oily compound having strong lemon-like odor. Of course, it is found in lemongrass, which contains about 60 to 80% of citral. It has industrial application and used for the synthesis of beta-enone, which is required in the perfume industry. This is a citral. Okay. This carbon atom 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the 10th carbon atom. Thus there are 10th carbon. I have shown also the positions of the carbon atoms, and therefore at this is a 1, 2, 3 methyl group at 3 position, then another methyl group is at 7 position, and double bonds. One double bond starts from 2nd position and another starts from 6th position. Okay. Let us see the constitution of citral. Okay. Now the structure of citral has been established by the analytical method, and finally it is confirmed by its synthesis. Now the analytical method consists of this step. The first molecular formula is determined by the procedure, and the molecular formula of citral is found to be C10. I have calculated the 10 carbon atoms, hydrogen 16 and 1 oxygen atom. Okay, as I tell aldehyde, 1 oxygen atom is there. Now the second step is citral is unsaturated. What is the reaction for unsaturation? That is test bromine water test. When bromine is reacted with the molecule, it forms adduct. When it is one double bond is there, dibromo derivative. When two double bonds are there, tetrabromo derivative adduct is formed. Here, citral on reaction with bromine gives tetrabromo adduct. This is a tetrabromo adduct. Reaction of the citral with bromine addition. Tetra indicates that there are two double bonds. Second reaction, on hydrogenation, this is citral, it consumes 2 molecules of hydrogen and thus forms tetrahydroadduct. It means that citral contains 2 double bonds. Now, yes, it is an aldehyde. How it is proved? Reaction first. It reacts with hydroxylamine. This is the reaction with hydroxylamine forming addition, reaction forming oxime as a product. While on a reaction with sodium bisulfite, it forms bisulfite. And this reaction indicates that citral must be having carbonyl group, because formation of oxime is the reaction of carbonyl group. Okay. Now, second reaction. controlled oxidation of citral with moist Ag2O produces gyranic acid containing the same number of carbon atom as that of citral. Oxidation do not loses the any carbon atom. Therefore, this is a 10 carbon atom of citral. Controlled oxidation, acid is formed having the same number of carbon atom, gyranic acid. Yes, what is the reaction? RCHO on oxidation gives RCOOH. That is, aldehyde on oxidation gives acid. Thus, citral is an aldehyde, gives acid. While on reduction with sodium amalgam in dilute acid, citral produces primary alcohol. Primary alcohol RCHO on reduction RCH2OH, and therefore this is a geraniol is an alcohol. Therefore citral gives on oxidation acid and on reduction gives alcohol, and this indicates that citral is an aldehyde. Very important reaction, it is asked. Now the next analysis is citral is acyclic. Now we have seen in the previous step, citral contains two double bonds and aldehyde group in the molecular formula C10H16O. It indicates that it is a derivative of alkane having the formula when n equal to 10. What is the formula of alkane? Becomes CnH twice n plus 2, n equal to 10, and therefore C10H22. The corresponding general formula of alicyclic alkane, it is the corresponding general formula of open chain alkane. Now look on the citral C10H16O. Why 4 hydrogens are less? Due to the presence of two double bonds, carbon-carbon double bond. Again, why 2 hydrogen atoms are less? Due to the presence of oxygen. And if these are contributed, then the formula matches with the formula of acyclic alkane. And therefore, open chain alkane, that is the citral, is acyclic. Now, further point is, what is the carbon skeleton of citral? Now, the first reaction, when heated with potassium hydrogen sulfate, this is a potassium hydrogen sulfate, delta indicates heat, dehydration takes place, citral loses the molecule of water, and thus this is the molecule of water removed, forming the structure, known structure paracymene, forming the known compound paracymene. Look, this is the structure of paracymene, and therefore this type of structure, but acyclic structure, may be present in citral. Second reaction, citral contains 2 molecules of ozone during ozonolysis and forms a mixture of acetone, aldehyde and glycol. This is a citral on ozonolysis consumes 2 molecules of ozone, that is twice O3. The first is acetone, this is aldehyde and this is a glycol. These products and the first product, that is close look at the structure of paracymene and the product obtained on ozonolysis, we can have the carbon skeleton of citral in which 2 isoprene units are joined by head to tail arrangement. Look here, this is a head of one isoprene unit joined to the tail of another isoprene. This is a one isoprene unit. Here tail, head of the another isoprene unit, This is a head, branched end is a head, another is a tail. Look here the same way. This is the branched end is a head, another is tail. Tail is linked to the head of the another, and therefore citral contains two isoprene units joined together in head to tail fashion. Now we have seen the citral contains double bonds. What is the position of double bond? Okay, and therefore here the position of double bond is located. On treatment with sodium bisulfite, citral forms mono as well as dibisulfite adduct. Addition product is formed. And this is the character reaction of alpha beta unsaturated aldehyde. This is the aldehyde group and this is alpha beta unsaturated aldehyde. Therefore, 1, 2 alpha beta aldehyde gives this type of reaction and therefore citral must be an alpha beta unsaturated aldehyde. Further, citral shows UV absorption at 235 nanometer. This again confirms the presence of alpha beta unsaturated aldehyde. Second reaction, on boiling with potassium carbonate K2CO3 solution, citral forms two compounds, namely 6-methylheptanone, that is a 6-methylhepta-5 2O. The positions of methyl group is 6, the position of double bond is 5, and the non group methylheptanone, that is ketone group, is at a 2 position, and acetaldehyde, this is a acetaldehyde. Okay, and therefore citral on this reaction gives these two products, and the formation of these two products suggests that the second double bond, first double bond is at alpha and beta position, while the second double bond is at 6, between 6 and 7. Okay, and therefore thus the position of double bonds are located, and therefore two double bonds are located. Now, on the basis of these evidences, scientists Semler and Werle proposed two different structures which differ only in the position of double bond. Look here, Werle given this type of structure, here double bond, one double bond and second double bond, while Semler gives this structure double bond, double bond. Okay. Now, which is the correct structure? Oxidation study. Oxidation of citral using alkaline potassium permanganate followed by chromic acid. This is a potassium permanganate followed by chromic acid. Gives a mixture of acetone, levulinic acid, oxalic acid. These three products are obtained by the oxidation of citral. How these three products are obtained? Look on the structure. This is the breaking of this bond forming oxalic acid. Breaking of this forming acetone, and remaining is the levulinic acid. This carbon is oxidized. Okay, this. Here, how the products of oxidation and ozonolysis are formed with the reaction of citral. Here the oxidation of citral giving acetone, linolenic acid and oxalic acid, these three products of oxidation, while on ozonolysis it consumes two molecules of ozone. This is the first molecule forming acetone, this is the linolenic acid aldehyde, and the formation of glycol by consumption of second molecule. Okay. Now this structure of citral is confirmed by its synthesis and therefore synthesis of citral. The first method is Barber-Bourvelt synthesis. It involves the following steps. The first step is the synthesis of methylheptanone. It is done by the reaction of 2,4-dibromo 2-methylbutane with sodium-acetyl acetone. Elimination of sodium bromide takes place. Here, look here. This is a CH3, and here this Br, NaBr is eliminated and the formation of this product. The ketonic hydrolysis of this forms the ketone, here the ketone. Thus, methylheptanone is formed. Now, from this methylheptanone, the synthesis of calcium granate is obtained. This is done by reformatory reaction. Okay, here this methylheptanone on zinc and iodo derivative of ethyl acetate, the reformation reaction takes place forming this product, hydrolysis. Okay, and finally the reaction of the formed product with acetic anhydride. This is a acetic anhydride giving the ester product. This ester on hydrolysis gives acid, and the reaction of this gyranic acid with calcium hydroxide, that is gives the calcium salt of gyranic acid, that is a calcium gyranate. Now in the third step, this calcium gyranate is treated with calcium formate. The distillation produces citral. Thus, the structure of citral is confirmed by its synthesis. This is the second method. This is for you for homework. Study this reaction, same reaction. This is the first acetylation. Here addition takes place. Okay, partial reduction of this bond, one bond, and therefore CH2. Allylic rearrangement takes place. Then this sodium derivative of acetoacetic ester get attached to this with the elimination of NaBr. And the hydrolysis and decarboxylation gives methylheptanone. In the second step, this methylheptanone is treated with ethoxyacetylene magnesium bromide. This is a ethoxyacetylene magnesium bromide. Okay, here again the product is partially reduced and finally allycyclic rearrangement gives citral. Now the reaction of citral which we have studied in the analytical evidence are shown here by using the structural formula of citral, that is citral contains aldehyde group. Aldehyde on reduction gives alcohol, primary alcohol, this is the reaction, while on oxidation gives acid, this is the reaction. Second, the formation of methylheptanone from citral is shown, while the formation of this is acetone, oxalic acid, and yes, we have seen the linolenic acid by the oxidation with KMnO4 followed by chromic acid. Then ozonolysis reaction, that is we have seen in detail. And final is the heating with potassium bisulfate giving the paracymene-like structure. Thus, these reactions confirm the structure of citral which is obtained from synthesis. Now, citral exhibits geometrical isomerism. Here, there are two forms of citral are observed. Cis-citral is known as a neural, while trans-citral is known as a geranyl. And these two isomeric forms are confirmed by NMR spectra. Now, the citral isolated from natural source is a mixture of first isomer, that is cis isomer 10% and trans isomer 90%. Okay, and therefore this is the due to the double bond, these two are varying in the structure, and therefore these are geometrical, that is cis trans isomers. Okay. Now, uses of citral, it is widely used as a flavoring agent and in the preparing synthetic perfumes, also employed in the manufacture of geranyl. With this, we complete the first natural product from terpenoid, that is a citra. Students, with this I conclude my lecture. Thank you.